Hello and welcome back. In this session, we're going to look at concavity of functions and points of inflection. So we have a function here, and I call it y equal to 1 over 2x. So it's a straight line that's drawn here in the xy plane. As you can see, this point 2 corresponds to this point 1, so the slope is 1 over 2. So it's a straight line, and we want to find out what happens if the slopes change. So let's start with point 2 here. X equal to 2, value of y is 1. So let's go to point 4. At point 4, the slope of the line is still half. But let's assume that means between 2 and 4, if we were to graph the slope, it will be this dotted line. The slope will stay along the dotted line. It will be still 1/2. Well, let's say we want to make at 4, the slope to be more than 1/2. So in other words, this point that I have here, it will move somewhere out here. So in the process, the dotted line will be replaced by this new line. So if I change the slope progressively between 2 and 4, continuously increase it so that I reach this point with a higher slope at 4, then it should go like this. It should go a little bit curve up. Similarly at 6, if I want the slope to be a little bit more, then the curve will start, the line will start curving even more. So you can see in the process, if I require that the slopes progressively increase as I go from left to right, if I increase the value of x, you can see the curve, the line starts curving up. And that is what we call concave up. So concave up is when the curve starts curving up and its slope starts increasing. So graphically, that's obvious what happens. Numerically, what we do is we take any 2 points, x1 and x2, and let's say x1 is less than x2, and we find the value of the slope at the point x1, call it f1, f prime of x1, and we also find the slope at point x2. And then we compare them. Since we require the slope at the x1 point be less than the slope at the x2 point, so if we require that, then we can see that the slope is, the curve is going up. So that is concave up case. Now let's see what happens if we do the other way around. Let's start with point 8. At point 8, the curve still has the slope, this original curve still has the slope half. Let's say at 10, I don't want it half. I don't want this half to be the slope at 10, but I want it less than that half. So in other words, that point will start curving slightly downwards, and then it will go down. So if, again, looking at it numerically, if the value of the slope at point x1, that is, corresponds to x equal to 8, at this point, if the slope is more than the slope at point x2, then it is concave down. Now, for this kind of test to apply to a function, whether it's going up or down, we have to take 2 points, x1 and x2, and those 2 points should be taken arbitrarily. And this condition, whether concave up or concave down condition, should hold good in any case. Now, in practice, we don't sometimes want to compare. We want to do it test at one point, whether it is a concave up region or concave down region. Now let's look at this function, which is concave up, this curve, which is the derivative. In fact, both of these curves that I drew, they are the derivative of concave up and concave down function. So, which means the derivative of the derivative, which we call the second derivative, f double prime, at any point for this curved up case, at any point, will be greater than 0. So concave up also implies f double prime is greater than 0 at any point where the function is going to be concave up. And in the same way, this second case, this concave down case, since it is a decreasing function, f double prime will be less than 0. So there we have it. Concave up means f double prime greater than 0 at any point in some interval, and f double prime less than 0, on the other hand, means it is concave down. Now let's see what happens when a function changes from concave up to concave down. So in that case, what will happen? If you look at these two expressions here, initially, let's say it was concave up, so the derivative was increasing, and then it became concave down. It was decreasing. So it's an increasing and a decreasing case, and at the point where it changes from concave up to concave down, really what's happening is the double derivative, f double prime x, is equal to 0. And that point where the second derivative becomes equal to 0 is called point of inflection. So that's all for this session on concavity inflection. Make sure to watch the next video on in which I will solve a problem using these concepts.